In early November 2016, a 12-meter carbon fiber tank sat in the SpaceX Hawthorne facility, undergoing initial pressure testing successfully, with some initial cryogenic tests completed and full cryogenic testing planned afterward. The test succeeded, the material worked, and for one brief moment, the future of Mars colonization was about to be locked into the wrong decision forever. Because that tank, destroyed later in 2017 in an intentional burst test, represented a path SpaceX nearly committed to completely. Carbon fiber composites cost $200 per kilogram. They weakened at cryogenic temperatures. They required weeks of careful layup in specialized facilities. But none of that mattered in early 2017 because the tests looked good enough. Then came December 2018, when Elon Musk fired off a tweet that changed everything. The entire vehicle, he announced, would switch to 300 series stainless steel. Not carbon fiber, not advanced composites. Steel. The same material used in grain silos and water towers. At Starbase in Boca Chica, Texas, sitting at coordinates 25 degrees, 59 minutes, 55 seconds north, 97 degrees, 18 minutes, 37 seconds west, the gamble on carbon fiber died, and the real Starship program began with a material that cost approximately $3 per kilogram, a roughly 66 times price difference that made rapid prototyping financially viable. But the economics told only half the story. Steel's cryogenic strength increased 200% at the temperatures liquid oxygen and methane required. Carbon composites weakened. Steel tolerated temperatures exceeding 1,000 degrees Celsius, eliminating the need for heat shielding on the leeward side entirely. Musk later called the steel decision the best one he made for the entire project, because what looked like a step backward was actually the only path forward to reusability at scale. By January 2019, the official confirmation landed. Stainless steel's thermal properties outweighed the mass penalty from steel's higher density, though thinner gauge construction mitigated the weight increase. The material could handle both the frozen propellants inside and the scorching re-entry plasma outside without expensive protective layers. The original plan called for a double-wall skin design with micropores, where fuel or water would evaporate through tiny holes on the windward side during re-entry, creating a cooling boundary layer. Elegant in theory. Abandoned in practice when ceramic tiles proved more reliable. But the manufacturing advantage sealed the deal. Carbon fiber required specialized facilities, trained technicians, and weeks of careful layup for each component. Steel enabled SpaceX to build a mill right at Starbase, producing sections daily instead of waiting months. The strategic goal wasn't just reaching orbit, it was enabling same-day reuse. Not the months of refurbishment required by the space shuttle. Not even the weeks needed for Falcon 9 boosters in the early days. Hours. The kind of turnaround time that makes Mars colonization economically possible when you need to launch hundreds of missions. Steel made that timeline conceivable because you could build fast, test fast, fail fast, and iterate faster than any competitor still babysitting composite layups in clean rooms. The engine count never sat still. In the 2017 BFR design, the upper stage carried multiple Raptor engines in various configurations, with early concepts featuring combinations of sea-level and vacuum-optimized variants. The configuration aimed for engine-out capability, meaning the vehicle could lose one or even two engines and still complete its mission. More engines meant more redundancy, but also more complexity, more mass, more potential failure points. By 2019, the upper stage design settled on 6 Raptors total, 3 sea level, 3 vacuum. The reduction saved mass without sacrificing the mission profile, because SpaceX refined the engine reliability to the point where earlier configurations felt like overkill. Then came the naming shift in 2018 when Musk rebranded the entire system. Starship became the upper stage, the actual spaceship. Super Heavy became the booster, the rocket needed only to escape Earth's gravity well. On Mars, on the Moon, anywhere with lower gravity, you just needed Starship itself. The branding clarified the architecture, and the Super Heavy booster underwent its own engine shuffle. Early plans in the 2020s called for 31 Raptors, then the design pushed to 33, with considerations for configurations up to 35 engines maximum, though not all would fire on every flight. The current configuration uses 33 operational Raptors, each producing 230 tons of thrust. Multiply that out and you get over 7,500 tons of combined thrust at liftoff. More than the Saturn V, more than the Space Shuttle, more than anything that had ever flown. But the fluctuating numbers revealed the constant optimization happening behind the scenes, balancing thrust against weight, redundancy against complexity, cost against capability. And every change set the stage for the explosions to come. The heat shield underwent its own transformation in 2019. The double-wall micropore concept, where fuel or water evaporated through tiny holes to cool the windward side during re-entry, gave way to reusable ceramic tiles, similar to the Space Shuttle's thermal protection system. The tiles covered the hotter areas, particularly the belly and nose, where plasma temperatures peaked during atmospheric re-entry. More proven technology, less elegant but more reliable. The same year, the body flaps evolved from 4 to 2, weight savings without compromising control authority during descent. Then came 2021 and the strangest design change in the program's history. The nose cone got pointier. Not for aerodynamic reasons, not for thermal management, for intimidation. Musk confirmed the inspiration came from Sacha, Baron Cohen's 2012 film The Dictator, specifically Admiral General Aladdin's line about rocket design. Round is not scary, pointy is scary. So the nose cone became pointier. No, performance impact, pure aesthetics and psychology. But underneath the comedy beat, the September 2019 Musk presentation at Starbase detailed the serious engineering behind orbital refueling. Up to 8 tanker flights would be required to fully fuel a Starship headed for Mars. Each tanker would launch, rendezvous in orbit, transfer propellant, and return. The architecture assumed reusability at every step, and the destinations stretched beyond Mars. Anywhere in the solar system became theoretically accessible with enough refueling stops. The tiles, the flaps, the pointy nose, all served a vehicle designed not for one-off missions, but for routine operations across interplanetary distances. November 20th, 2019. The Mk1 prototype sat at Starbase undergoing a cryogenic proof pressure test when the tank ruptured. Metal tore, propellant vented. The prototype was destroyed in seconds. Mk1 never flew. Mk2 got abandoned before testing even began because the design had already evolved past it. Then came the SN series, serial numbers, ship iterations. SN1 destroyed in a pressurization test in February 2020. SN2 actually survived its pressure test, a brief victory. SN3 destroyed in another pressure tank test. SN4 completed multiple static fires successfully, validating engine integration and fueling procedures, then exploded during a post-static fire test. 5 major prototypes lost between late 2019 and mid-2020. But August 27th, 2019 had already provided the first real success. Starhopper, the prototype that looked more like a water tower than a spaceship, completed a 150-meter hop test. It lifted off, slewed sideways under the thrust of a single Raptor engine, then settled into a soft landing. The stainless steel structure held, the flight controls worked. 3 Raptor engines had been tested across Starhopper's campaign. The foundation was validated. Everything that came after, every explosion, every incremental improvement, built on that initial proof that steel could fly. The SN series failures weren't setbacks, they were data. Each destroyed prototype revealed weak points in tank construction, weld quality, pressurization systems. The philosophy was fail fast, learn faster, and the explosions were just getting started. September 3rd, 2020, SN6 lifted off, flew 500 feet, and landed intact, building on Starhopper's success, proving the design could be replicated. Then came December 9th, 2020, and SN8 changed the game. First prototype with aerodynamic fins, first with a nose cone. SN8 climbed to 7.8 miles, 12.5 kilometers, higher than any Starship prototype had ever flown. The ascent worked. The belly flop maneuver worked, flipping the vehicle horizontal to increase drag during descent. But the landing burn failed. The header tank, a smaller reserve tank meant to provide propellant for the final landing engines, lost pressure. SN8 descended too fast and exploded on impact. Spectacular failure, invaluable data. March 30th, 2021 brought SN11 to approximately 10 kilometers altitude before an engine relight failure caused a mid-air explosion during descent. The vehicle disintegrated in fog so thick ground, cameras barely caught the moment. Debris rained down. Another total loss. SpaceX skipped SN12, SN13, and SN14 entirely. The gaps in serial numbers marked major design revisions, incorporating fixes for the header tank, pressure issues that killed SN8, and the engine relight problems that destroyed SN11. The high-altitude test campaign revealed the brutal difficulty of controlled re-entry. Body flaps had to maintain stability during hypersonic descent. Raptor engines had to relight reliably after the stresses of ascent and the cold soak of high altitude. Every failure narrowed the problem space. Every explosion brought knowledge that couldn't be gained any other way. May 5th, 2021. SN15 climbed to 10 kilometers, performed the belly flop, reignited its engines, and landed. Not perfectly. A small fire burned at the base for several minutes after touchdown, but the vehicle stood, intact, the first complete success after so many explosions. SN15 validated the body flaps, proving they could control a falling skyscraper through transonic and subsonic regimes. It validated Raptor relight capability, the critical technology needed for landing on Earth, Mars, or anywhere with an atmosphere. The early high-altitude test phase ended with approximately 29 ship prototypes tested by 2024, counting Starhopper, the MK series, and the entire SN run. Each one a stepping stone, each failure a lesson. SN15's success didn't mean the vehicle was ready for orbit. It meant the fundamental challenges of atmospheric re-entry and powered landing had been solved at the prototype scale. But orbit required something much larger. It required super heavy, and it required integrating the 2 stages into a single system that could survive staging, re-entry, and landing. SN15 marked the end of the beginning. The integrated flight tests were about to start. April 20th, 2023. Ship 24 sat stacked atop Super Heavy Booster 7 at Starbase, the first integrated flight test. IFT-1, 33 Raptor engines ignited. The stack lifted off. For 4 minutes, it climbed. Then the stage separation sequence failed. The 2 stages didn't separate cleanly. The vehicle tumbled. The flight termination system activated. Explosion. But the launch pad survived. The ground systems worked. The tower stood ready for rapid reuse, despite the vehicle's destruction. November 18, 2023 brought IFT-2. This time, the stack reached 93 miles, 150 kilometers, outer space. The first Starship to cross the Kármán line, but the mission ended early with another explosion before splashdown. Progress. March 14, 2024, an IFT-3 experienced a booster rapid, unscheduled disassembly at approximately 1 minute into flight at low altitude. Another setback, but each test provided critical data on ascent anomalies, engine performance under full stack conditions, and staging sequences. The failures weren't random. They were systematic, revealing specific problems that could be addressed, and underneath all the testing pressure sat the NASA Artemis HLS contract. Starship had been selected as the lunar lander for Artemis 3. The program timeline had already slipped to 2028, partly because Starship's development couldn't be rushed. Each explosion bought knowledge, but also burned time. The integrated flight test era had begun, and it was going to be a long road to reliability. June 6, 2024, IFT-4, full ascent burn, super heavy booster, completed its flip maneuver, reignited engines, and performed a soft splashdown in the Gulf of Mexico. Not a landing, a controlled water impact. Meanwhile, Starship upper stage continued to orbit, re-entered over the Indian Ocean, and also achieved a soft splashdown. Both stages survived re-entry. Both demonstrated controlled descent. The first time, both halves of the stack made it through the entire flight profile without exploding. Then came October 13th, 2024, IFT-5, the day everything changed. 33 Raptor engines fired without a single failure. The booster separated, flipped, and began its descent back to Starbase. But this time, it didn't aim for the Gulf. It aimed for the launch tower. Mechazilla. The massive arms built into the launch tower itself, designed to catch a returning booster in midair. The booster descended on 3 engines, performing the landing burn with precision. The chopstick arms closed. Contact. The booster was caught, 70 meters tall, 23 stories, 5,000 tons when fully fueled, caught out of the sky like a falling pencil. Meanwhile, ship completed its mission, splashing down in the Indian Ocean as planned. 0 engine failures across all 39 Raptors between both stages. The catch revolutionized the entire concept of launch cadence. No landing legs to deploy and retract. No complex ground equipment to transport the booster back to the pad. Just catch it, inspect it, refuel it, and fly again. Hours instead of weeks. The paradigm had shifted. November 19th, 2024, IFT-6. The booster latched onto the catch tower during descent, but mission control diverted it to a Gulf splashdown as a precaution. Something in the telemetry wasn't perfect. Better safe than sorry. But the ship achieved something new. In space, one of its 6 Raptor engines ignited. The first successful in-space engine relight, critical for orbital maneuvering, for lunar missions, for Mars transfers. The ship then re-entered and splashed down in the Indian Ocean, completing another controlled descent. Progress continued through subsequent test flights as SpaceX refined the vehicle systems and operational procedures. The integrated flight test campaign was proving that reaching orbit consistently required solving problems that only appeared at full scale under full thrust, with real propellant flowing through real engines in real time. No amount of ground testing could replicate the exact conditions. Each flight bought data that couldn't be purchased any other way. The program demonstrated both triumphs and setbacks in equal measure as testing continued. Booster reuse concepts were validated through multiple catch attempts and refinements to the Mechazilla system. Ships continued to push the boundaries of re-entry survival and controlled descent. Progressive improvements in engine reliability, propellant management, and flight control systems emerge from each test campaign. The strategic validation of catch and refly operations proved the concept worked, even as individual flights encountered challenges. By late 2024, multiple integrated flight tests had been completed, with several achieving full mission success, including the revolutionary October 2024 booster catch, the single most important breakthrough in the program's history, because catching a booster mid-air, refurbishing it in hours instead of weeks, and flying it again transformed the entire economic model of spaceflight. The successful demonstrations proved the concept worked and validated the path forward. In 2024, SpaceX announced Starship version 2, 1.8 meters taller than the original. New forward flap design specifically engineered to reduce re-entry heating on the control surfaces. Increased propellant capacity for extended mission duration, and higher payload capability. Higher thrust from continued Raptor engine iterations, with Raptor 3 variants targeting 330 seconds of specific impulse. Version 2 deployed starting with Ship 33 onward. The mass-to-orbit improvements were still being validated in flight tests, but the design refinements addressed lessons learned from the first 29 prototypes and multiple integrated flights. The forward flaps had proven vulnerable to plasma heating during re-entry on multiple flights. The new design moved them slightly, changed their geometry, and added reinforcement. Small changes, potentially massive impacts on re-entry survival rates. Throughout 2023 to 2025, minor structural modifications continued. Adjustments to the catch arms based on IFT5 data. Grid fin tweaks on the booster for improved control authority during descent. Incremental improvements that didn't warrant new version numbers, but collectively refined the vehicle. Version 2 wasn't a revolutionary redesign. It was the culmination of every explosion, every near miss, every successful test distilled into a slightly better vehicle. The kind of iteration that only happens when you build and fly prototypes faster than your competitors can complete design reviews. The Raptor engine itself underwent its own evolution from 2016 onward. The first versions were tested at the SpaceX Hawthorne facility alongside those doomed carbon fiber tanks in 2017. Full-flow staged combustion cycle. Both propellants, liquid oxygen and liquid methane, fully gasified before entering the combustion chamber. Maximum efficiency. Unprecedented complexity. No engine had ever flown with that cycle before Raptor. By the early 2020s, Raptor 2 achieved 230 tons of thrust per engine. The target for Raptor 3 pushed specific impulse to 330 seconds, a measure of propellant efficiency that directly translated to payload capacity and mission range. Every second of specific impulse gained meant more mass to orbit or more delta for interplanetary transfers. Engine iterations enabled the Super Heavy thrust optimization. 33 operational Raptors, producing approximately 7,590 tons of combined thrust at liftoff. More than enough to lift the fully fueled stack, and Raptor reliability became critical. IFT-5 achieved zero engine failures across 33 booster engines and 6 ship engines, 39 engines firing without a single shutdown. That reliability number, 0 failures, mattered more than any thrust increase or efficiency gain, because reusability only works if the engines don't explode. The Raptor evolution mirrored the Starship evolution. Rapid iteration, constant testing, incremental improvements compounding into revolutionary capability. Stainless steel at approximately $3 per kilogram versus carbon fiber at $200 per kilogram. Roughly 66 times cost reduction. That single number enabled everything that followed. Approximately 29 Starship upper stages tested from 2019 to 2024. Starhopper, the MK series, the entire SN run. 5 major prototypes destroyed in the 2019 to 2020 timeframe alone. 3 successful hop tests at approximately 500 feet. Multiple high-altitude flights reaching up to 12.5 kilometers. Multiple integrated flight tests from 2023 through 2024. Several full mission successes. 1 booster catch success that revolutionized reusability. The NASA Artemis HLS contract selected Starship as the lunar lander, but the program slipped to 2028 because development couldn't be rushed. 8 tanker flights required for Mars refueling architecture. Each tanker launching, rendezvousing in orbit, transferring propellant, and returning. Mars missions viable by the 2030s per Musk projections, assuming the refueling architecture worked and Starship achieved the same-day reuse that steel made theoretically possible. Competitors still measured turnaround in months. Super Heavy booster stood 70 meters tall, 5,000 tons when fueled. Mechazilla catch arms grabbing it mid-descent. The scale defied belief, and the numbers told the story of a program that chose speed over caution, iteration over perfection, explosions over endless design reviews. Starbase at Boca Chica remains an active development and launch site. Public tours run regularly. Memorials mark the spots where prototypes exploded. SN8 has a commemorative plaque. The wreckage of early failures sits in designated areas, rusting monuments to the fail-fast philosophy. Museums host Raptor engines. Kennedy Space Center Visitor Complex displays cutaway versions showing the E's, full-flow staged combustion internals. Starhopper, the stubby prototype that started it all, sits preserved at Starbase as a historical artifact. Academia adopted Starship as a case study in rapid prototyping, contrasting it against traditional aerospace programs like the Space Launch System and its cost overruns. Engineering courses teach the iteration philosophy. Business schools analyze the material switch from carbon to steel as a pivotal strategic decision. Cultural impact spread through documentaries. Everyday Astronaut produced multi-hour deep dives into Starship development. Kerbal Space Program modders recreated Starship and Super Heavy for virtual missions. Eric Bergier's book Liftoff chronicled the early SpaceX years, providing context for the Starship program's roots. Industry debates rage. Steel versus composites for orbital vehicles. FAA regulatory delays versus innovation speed. The tension between moving fast and breaking things versus the government's mandate to protect public safety. But the paradigm shifts achieved cannot be debated. First stainless steel orbital class vehicle. First booster catch and reuse with hours of turnaround instead of weeks. Demonstrated path to Mars-scale payload capacity. Cost revolution with roughly 90% reduction in materials costs. On-site manufacturing enabling daily production versus weeks-long traditional processes. The program changed what was possible, and it did so by choosing the material everyone said was too simple, too heavy, too old-fashioned. That 12-meter carbon fiber tank sitting in Hawthorne in early November 2016 could have locked SpaceX into a dead end. Instead, the December 2018 tweet that announced stainless steel opened the door to everything that followed. Every explosion, every success, every caught booster. All of it traced back to the moment Musk chose $3 steel over $200 composites and called it the best decision he ever made.